Hello, Mrs. Boyd, and today we're going to talk about nuclear equations. Basically, nuclear equations represent changes that occur in the nucleus, and we're going to start off with some terminology that's really important. So first we're looking at things like alpha particle, which is basically a helium nucleus, can be represented in a couple different ways. Also a beta particle can be represented in a couple different ways. We're going to skip positron for now because you are not going to be doing any problems in my class, at least, on positron emission. Next, we're going to go down to neutron, and that is represented by that symbol there. And finally, gamma rays. So these are the things you're going to need to know to solve nuclear equations in biochemistry. Let's move down now a little bit to a review of atomic symbols and isotope forms. So we have pictured here a potassium. The symbol for potassium is K. And you notice in the lower left-hand corner we have a 19. That is a potassium's atomic number, also its number of protons, and that never changes for potassium. Meanwhile, in the upper left-hand corner, you have the number 39. This represents the mass number. That tells you how many neutrons plus protons you have in an element, and this can change. You can actually have various isotopes of potassium. So you can have potassium 40 or potassium 38. There's a lot of different isotopes of potassium. So that's just kind of to remind you what the symbols mean. Please also note that the 39 mass number represents neutrons and protons added together. So if, for example, I were to ask you on, an assignment exactly how many neutrons this isotope of potassium had, then all you would have to do is take out the protons out of that total of 39. So you would just do 39 minus 19 results in 20, and that tells you the neutron number. So hopefully that might be helpful for you on some questions that you might encounter. All right, so let's talk about 4 equations that you should be able to recognize. So first let's go through 2 different decay equations. The first is alpha decay and the second is beta decay. And basically these are naturally occurring nuclear phenomenon, and it's an element that is fairly large that is going to give off some kind of emission. And in this case, it gives off, as we mentioned earlier, a helium atom, which is also known as an alpha particle. And this is a form of radiation. In beta decay, you can see that instead of giving off an alpha particle, it gives off a beta particle. So the same identical isotope can actually go through alpha or beta decay. Every element sort of has a tendency to do either alpha or beta or both, or maybe it does positron emission, but there's just these clues are what you're really going to be looking for, though, when identifying what the isotope is doing. The second kind of type of equation that you should be able to recognize is called a fusion equation. And these are things that occur typically in the sun. So we don't really see a lot of this on Earth, but what's happening here is 2 smaller nuclei. So for example, here we have deuterium and tritium, 2 isotopes of hydrogen that combine together to make a helium atom and bump off also a neutron. Don't be confused, this looks like a helium ion that was given off during alpha decay, but the key here is you have 2 smaller elements on the left-hand side of the equation fusing together to make the larger helium. Finally, the last category here is going to be our fission reactions, and these occur in bombs and nuclear power plants. Oh, by the way, fusion and fission, highly energetic reactions. This is why we don't do many labs during the nuclear unit, because we can't possibly tolerate that kind of energy release. But we have here a uranium atom, and you will notice that it breaks down into 2 smaller atoms. So fission, just kind of the name kind of implies, is fizzing or breaking apart a larger atom. And this is usually triggered by a neutron, and then likewise releases a few neutrons that can cause a chain reaction. Oh, one thing I forgot to mention back up here with beta decay. So interesting what's happening here. This uranium that you'll notice goes from 235 to Neptunium 235. But you notice, of course, the proton number has to change because the element changed. But what's interesting is that a neutron changed into a proton in this reaction. And so that's why you got a change in the proton number, but you didn't get an overall change in the mass number. So that's something to kind of notice about beta decay. Okay, all right, let's go down and work a couple of examples. So let's take the first example. We have copper 64, and it looks like it's giving off some kind of particle here. Hopefully you're now starting to become familiar with the fact that that is a beta particle. And the way that you solve these equations is basically you're going to solve all of the mass part of the problem, and then you're going to also then switch over and solve all of the proton part of the problem. So let me show you exactly what I mean by that. So first we have to remind ourselves that an arrow indicates something really important. It means that a reaction has occurred, and you have to know that the left side and the right side balance out. So please do not lose any protons or neutrons in this process, because we cannot create nor destroy matter. So with that in mind, let's go ahead and figure out, if we have 64 on the left, that is our mass number. We have 29 protons. We better make sure that on the right we have the same exact system. So 0 plus what number gives us 64? And of course the answer is 64. Likewise, 29 minus 1 equals 28. So we have 64 and 28 is what we need to write in this box up here in order to keep this an equation balanced. So 64 and 28. The only thing we're missing now is what is the other element that was formed out of this beta decay of copper. So let's head down to our periodic table here and let's look for element number 28, and we see that it is nickel. So we're going to go ahead and head back up, and we're going to put a Ni in that spot. Okay, hopefully you see how I did that. Let's go ahead and move down to the second problem that we are going to solve, and that is the uranium-235 gets bombarded with a neutron. So our first clue here is that we have a neutron in play. So we have stimulated a reaction to occur, and it looks like on the right hand side we have krypton, and then we also have 2 neutrons liberated. So let's see if we can figure out exactly what's going on here. Again, we have to have the left and the right side have to be completely, sorry, my fingers today are just, I guess they're too dry and they're just not letting me move very easily. But we have 235 plus 1 equals 236, and I got that from adding these two numbers together. Then on the bottom I have 92 plus 0. So 92 plus 0 equals 92. So we have to make sure that on the right-hand side we also have 236 and 92. So far we have 95 from krypton plus 2 from the neutrons. Make sure that you distribute that 2 throughout the neutrons over there on the right. And on the bottom we have 36 plus 2 times 0 is 0. So we have 97 and 36. Now that does not equal 236 and 92, does it? So we have to figure out what the heck can we add to that 97 to get up to 236. And hopefully you guys recognize that that is a simple subtraction problem. So 236 minus 97. So go ahead and pull up your calculator. 236 minus 97, don't want to forget, keep saying it to myself here. 236 minus 97 equals 139. So we're going to pull that back into our Notability doc. And we're going to put it up here in the left-hand corner. 139. All right, let's do the same thing on the bottom. So 92 minus 36. So 92 minus 36 equals 56. So we'll head back over again to Notability, and that's going to go on the bottom. All right, so let's go down to our periodic table and figure out what 56 is. And it looks like 56 is barium. So barium has 56 protons, so that's how we know that that is the atomic number 56. Barium. All right. So I'm just going to go ahead and highlight our answers here because this is what you're going to be asked to fill in as you go through these problems. All right. Oh, by the way, what is this? Is this a fission, fusion, or a decay problem? So it looks like uranium is being bombarded with a neutron and then it's being split into two smaller. So hopefully you're getting the idea here that this is going to be a fission problem. All right, and let's work our final example. Ooh, we have gold. So gold is changing into something, or it's decaying into something. Let's see what's happening here. We have, as you can see right here, a helium nucleus, and so that is an alpha particle. So we're going to take that alpha particle, and automatically that's going to tell us that that is alpha decay. So we have alpha decay going on here. And again, everything on the left has to equal everything on the right. So this was probably pretty easy to solve by hand. So we have 185 on the left. So we only have 4 on the right. What the heck? So we have to add a lot. We have to add 181 to that mass number. Similarly, we have 79 on the bottom, that is gold's atomic number, minus the 2 from helium, and that is going to give us 77. We need 77 more protons to balance this all out. So let's go down here and see what number 77 on the periodic table is. It looks like it's iridium. That's not an element we hear about very often. So iridium. And that is our final answer there for our alpha decay problem. So hopefully this will help get you started on how to balance nuclear equations.